Hello friends, IBM is here with another episode of Learning Physics. This is AS Physics 9702 multiple choice questions. These are for paper 1. My name is IBM and without wasting time, I would like to take you to part 2 of solved past paper questions in errors and uncertainties. So without wasting time, let's move to the document. This is AS Physics 9702 multiple choice questions, and we are dealing with errors and uncertainties. So far we have done part 1, and I think we stopped on page 19. Let's start from page 19. So we stopped on page 19, I guess. So we should move to page 20. A quantity y is to be determined from the equation y is equal to p times x q over q squared. The percentage uncertainty in P, X, and Q as shown here. What's the percentage uncertainty in Y? So we now know that percentage uncertainty in Y is going to be percentage uncertainty in P plus percentage uncertainty in X plus twice percentage uncertainty in Q. So this will be for P, that is 6, for X, that is 2, for Q, that is 2 times 4, which is 8 plus 8, which is 16%. So the answer is C. A thermometer can be read to an accuracy of plus or minus 0.5 degrees Celsius. The thermometer is used to measure the temperature rise from 40 to 100 degrees Celsius. What is the percentage uncertainty in the measurement of the temperature rise? So let's first find the temperature rise. The temperature rise is going to be 100 minus 40, which is 60%, 60 degrees Celsius. Then the uncertainty, so this is the change in temperature, or the temperature rise. Then the absolute uncertainty in temperature, let me just use T for change in temperature or temperature rise. Then absolute uncertainty in temperature is going to be the uncertainty adds up. So this will be 0.5 plus 0.5, which is going to be 1.0 degrees Celsius. So as a percentage, so this will be 1 over 60 times 100. 1 divided by 60 times 100, that is 1.6 recurring, 666 recurring, which is 1.7%. So the answer there is D. The resistance of a lamp is calculated from the value of PD across it and the value of the current passing through it. Which statement correctly describes how to combine the uncertainties in the PD and in the current? So resistance is V over I. Add together the actual uncertainty in the PD and the actual uncertainty in the current. So that is not going to be true. This will be fractional uncertainty in V over V plus fractional uncertainty in I over I. This is going to be fractional uncertainty in R over R, which is the same as percentage in R is going to be percentage in V plus percentage in I. Add together the percentage in the PD and the percentage in R. That is true. So the rest, even if I don't check them. A steel wire is stretched in an experiment to determine the Young modulus for steel. The uncertainties in the measurements are given below. The load on the wire, the length of the wire, the diameter of the wire, the extension of the wire. What is the percentage uncertainty in the Young modulus? Young modulus is stress divided by strain. Force over area, then times original length divided by extension. So it means the percentage uncertainty in Young modulus is going to be the percentage in F plus the percentage in area. No, area is equal to pi d squared over 4. So this part This is going to be F times 4 over pi d squared times L naught over E. So this will be 2 times percentage in D, then plus percentage in L plus percentage in E, which will be equal to F is 2 plus 2 times D, which is 1.5, plus L, which is 0.2, plus extension, which is 1. So this will be 2 plus 3.0 plus 0.2 plus 1, which is 6.2%. So the answer is D. The diagram shows part of the thermometer. What is the correct reading on the thermometer and the uncertainty in this reading? So this is the reading. So the scale here is 21, 22, 23, 24. So this is 24 degrees Celsius. We can estimate to half a division. Each division is 1 degree Celsius, so divide by 2, that is 0.5 degrees Celsius. So this is automatically going to be 24.0 plus or minus 0.5 degrees Celsius. So the answer is D. Because the uncertainty is to one significant figure. I've just estimated one division is 1 degree. One division is 1 degree Celsius. Because the divisions are large enough, uncertainty will be half a division. That's how I came up with 1 degree divided by 2, which is 0.5. 0.5 is to 1 decimal place, 1 decimal place. A number of decimal places should be the same for the uncertainty and the true value. Okay. The resistance R of a resistor is to be determined. The current I in the resistor and PdV across it are measured. The results with their uncertainties are shown here. What is the uncertainty in this value of R? So since we know that R is equal to V divided by I, then absolute uncertainty in R is going to be absolute in V divided by V plus absolute in I divided by I. Then I'll multiply this by the value of R. So absolute in R is going to be, for V, 0.5 divided by 15.0 plus 0.2 divided by 2.0, then multiply by the value of R, which is 7.5. So 0.5 divided by 15 plus 0.2 divided by 2 times 7.5, which gives us 1. So this is going to be plus or minus 1 ohm. In an experiment to determine the acceleration of free fall g, the period of oscillation t and length L of a simple pendulum were measured. The uncertainty in the measurement of L is estimated to be 4%. And the uncertainty in the measurement of t is estimated to be 1%. The value of g is determined using that formula. What is the uncertainty in the calculated value of g? The answers are in percentages, so percentage in g is going to be ignore 4 pi squared. That will be percentage in L plus percentage twice percentage in t squared, or twice the percentage in t because of the power on t. So this would be percentage in L, which is 4% plus 2 times 1, which gives us the answer as 6%. So the answer is D. A student takes measurements of the current in a resistor of constant resistance and PD across it. The readings are then used to plot a graph of current against PD. A student takes measurements of the current in a resistor of constant resistance and PD across it. The readings are then used to plot a graph of current against PD. There is a systematic error in the current. So we are plotting a graph of I against V. There is a systematic error in the current, so the graph must be having a y-intercept. How could this be identified from the graph? At least one anomalous data point that is not a systematic error. The systematic error makes all values to deviate in one particular direction. The data points are scattered, that is a random error. The graph is a curve, not a straight line. That may not be a systematic error because V is directly proportional to I. The straight line graph does not pass through the origin. That is a systematic error. A micrometer screw gauge is used to measure the diameter of a small uniform steel sphere. The micrometer reading is 5 plus or minus 0.01. What will be the uncertainty in the calculation of the volume of the sphere? I think we have answered a similar question. Volume of a sphere is now pi 4 over 3 pi r cubed, which we have seen is going to be pi d cubed divided by 6. So the percentage uncertainty in volume is going to be 3 times the percentage uncertainty in d, which will be 3 times absolute in d, which is 0.01 divided by d, 5.00, then times 100. So we have 3 times 0.01 divided by 5 times 100, which is 0.6%. So this is 0.6%. An uncalibrated analog voltmeter P is connected in parallel with another voltmeter Q, which is known to be accurately calibrated. For a range of values of PD, readings are taken from the 2 meters. The diagram shows the calibration graph obtained. So we have uncalibrated meter P, scale reading, and the calibrated meter Q, scale reading. The graph shows that meter P has a zero error. The graph shows that meter P has a zero error. This meter is now adjusted to remove this zero error. When the meter is recalibrated, the gradient of the calibration graph is found to be unchanged. What is the new scale reading on meter P when it is used to measure a PD of 5 volts? So the graph shows the gradient does not change. So let's look for 5 volts. 5 volts. What is the new scale reading on meter P when it is used to measure a PD of 5 volts? So let's see 5 volts from Q. Calibrated meter Q, 5 volts corresponds to the scale on the X on this scale is the scale on the vertical axis is 2 divided by 10, that is 0.2. So this is 1, 2, 3, 4, 5. So this is going to be 7.0. But then remember the graph shows the graph here, the diagram shows the calibration graph obtained. An uncalibrated analog meter P is connected in parallel with another voltmeter Q, which is known to be accurately calibrated. For a range of values of PD readings, PD readings are taken from the 2 meters. The diagram shows the calibration graph obtained. The graph shows the meter P, that meter P has a zero error. This meter is now adjusted to remove this error. When the meter is recalibrated, the gradient of the calibration graph is found to be unchanged. The gradient of the calibration curve is found to be unchanged. Okay, so what is the new scale reading on meter P when it is used to measure a PD of 5 volts. So we have seen that, note that this one here is having is actually starting from 0. This is 0.123. So this is 0.3. So if it is reading 5 volts, it is actually going to be reading 5. 1, 2, 3. The true value is going to be 5.3, and 5.3 will give us a value here, which on the other scale is going to give us 7.2, 7.4. So because this has a 0, this is starting from 0.3. If it is recalibrated and the gradient does not change, so we shall just add a 0.3 the other side, so that it will give us 5.3, which reads 7.4 on the other scale. So therefore it means the new scale reading on meter P is going to be 7.4 volts. A student wishes to determine the density ρ of lead. She measures the mass and diameter of a small sphere of lead. What is the best estimate of the percentage uncertainty in her value of ρ? So I think we answered a similar question. It's determining the density. So density is equal to mass over volume, and it is a sphere. Volume is 4 over 3 pi r cubed, which is pi d cubed divided by 4. So the density is going to be 4m divided by divided by pi d cubed. So the percentage uncertainty in density will be percentage in m plus 3 times percentage in d. So this is going to be m 0.005 divided by 0.506 plus 3 times 0.02 divided by 2.20. And I will multiply this by 100 to change it to percentage. 0.005 divided by 0.506 plus 3 times 0.02, that is 0.06 divided by 2.2 times 100, which is 3.71. So this is 3.7%. So the answer is D. In an experiment, a radio-controlled car takes 2.50 plus or minus 0.05 seconds to travel 40.0 plus or minus 0.1 meters. What is the car's average speed and the uncertainty in this value? So average speed is going to be the distance over the time. So that is 40.0 divided by 2.5. I think the answer is 16. I don't even need to check that. 16.00 meters per second. I want the uncertainty. So uncertainty in speed is going to be absolute in d over d plus absolute in t over t. We multiply this by the value of the speed. So this is for d 0.1 divided by 40, for t 0.05 divided by 2.5, then times 16. 0.1 divided by 4 plus 0.05 divided by 2.5, then times 16. So that gives us, is it 20? No. 0.1 divided by 40 plus 0.05 divided by 2.5 times 16. So that is 0.36. 0.36 to one significant figure, that is 0.4. One decimal place. So the other one should also be to one decimal place, making the answer to be C. In an experiment to determine the acceleration of free fall using a falling body, what would lead to a value that is too large? Number one, air resistance. So we know that H is going to be equal to a half gt squared. So G is going to be twice H over t squared. Here we have assumed initial velocity is 0 using S is equal to ut plus a half at squared, where this was considered to be 0. So what would lead to a value that is too large? Number one, air resistance. Number two, dimensions of the body are too large. Number three, the measured distance is longer than the true value. G is directly proportional to the measured distance h. So if the measured distance is longer than the true value, it means G will be longer than normal. So the answer is going to be C. A mass is dropped from rest and falls through a distance 2 meters in a vacuum. An observer records the time taken for the mass to fall through this distance using a manually operated stopwatch and repeats the measurements a further 2 times. The average result of these measured times displayed in the table below was used to determine a value for the acceleration of free fall. This was calculated to be 9.8. Remember, the true value is 9.81, so that means this is very close. First measurement, second measurement, third measurement, average. Which statement best relates to the experiment? The measurements are precise and accurate with no evidence of random errors. That is not true. Although the difference between the measurements, of course, you notice, check the range. 0.73 minus the lowest, which is 0.59. The range is 0.73. 0.73 minus 0.59. So the range is 0.14. They may not be considered to be very precise, but at least, okay, the accurate within, of course, because they give an almost the same value of G, we can consider them as being accurate. No. This was calculated to be 9.81. Which statement best relates to the experiment? Number one, the measurements are precise and accurate with no evidence of random errors. The measurements are not accurate and not always recorded to the degree of precision. Okay, this is recorded as a whole number, not always recorded to the degree of precision of the measuring device, but the calculated experimental result is accurate. The calculated experimental result is accurate. I think that is true. It is 9.8, which is close to 9.81. So the answer is going to be B. The measurements are not always recorded to the degree of precision, which is true, but are accurate. Systematic errors may be present. There is nothing to show that systematic errors may be present. The range of results shows that there were random errors made, but the calculated value is correct, so the experiment was successful. There's nothing showing that there were random errors made here. Okay, so we can't see random errors from this because we are actually using just the value of time. We're just using the value of time to find G. So the most appropriate is B. The measurements are not accurate and not always recorded to the degree of precision of the measuring device, but the calculated experimental result is accurate. How do you see that the measurements are not accurate? You can verify and see if a half gt squared is equal to h, and h is 2 meters. It means the first value of t, if we know that g is supposed to be 9.81. So it means I will say t is going to be equal twice h over g under square root. We can check one value, 2 times h, which is 2, divided by what we expect, 9.81. 2 times 2 divided by 9.81, square root of the answer. So we expect our values to be very close to 0.64. Okay. What will reduce the systematic errors when taking a measurement? Adjusting the needle, I think that is automatically the same correct answer. Adjusting the needle on the voltmeter so that it reads 0 when there is no potential difference across it. In other words, we are removing the zero error. Measuring the diameter of a wire, that one reduces random errors. Reducing parallax, that is reducing random errors. Timing faint oscillations, that is random. So the answer is A. A quantity x varies with the temperature theta as shown in the figure. Theta is determined from the corresponding values of x by using this graph. X is measured with a percentage uncertainty of plus or minus 1% of its value at all temperatures. Which statement about the uncertainty in theta is correct? The percentage uncertainty in theta is least near 0 degrees Celsius. The percentage uncertainty in theta is least near 0 degrees Celsius. The percentage uncertainty in theta is least near 100 degrees Celsius. The actual uncertainty in theta is least near 0 degrees Celsius. I think this is true. The actual uncertainty in theta is least near 100 degrees Celsius. So the theta is determined from the corresponding values of x by using this graph. X is measured with a percentage uncertainty of plus or minus 1%. So that means the absolute in x is equal to 1 divided by 100 times the value of x. And we see that x is directly proportional to theta. X is directly proportional to theta. The absolute uncertainty of x is also going to be directly proportional to the absolute uncertainty in theta. That is actually the actual uncertainty, not the percentage uncertainty. So we are saying the percentage uncertainty in theta is least near 0 degrees Celsius. The percentage uncertainty in theta is least near 100 degrees Celsius. The actual uncertainty in theta is least near 0 degrees Celsius. So since it is a straight line through the origin, then the actual uncertainty in theta is going to be least near 0 degrees Celsius. So the answer here is going to be C. The measurement of a physical quantity may be subject to random errors and to systematic errors. Which statement is correct? Random errors can be reduced by taking the average of several measurements. That is very correct. Random errors are always caused by a person taking the measurement, not at all. A systematic error cannot be reduced by adjusting the apparatus, it can be removed. A systematic error results in a different reading each time. That's not true. It results into a systematic error results in a different reading each time the measurement is taken. Not at all. It results into the same reading but deviating from the true value. A quantity y is to be determined from the equations. Y is equal to that. The percentage uncertainty is in P, X, and Y as shown. What is the percentage uncertainty in Y? So percentage in Y is going to be percentage in P plus percentage in X plus twice percentage in Q. So this is 6 plus 2 plus 4 times 2, which is giving us 16%. So the answer there is D. The diagram shows an experiment to measure the speed of a small ball falling at a constant speed through a clear liquid in a glass tube. There are two marks on the tube. The top mark is positioned at 115 plus or minus 0.1 on the adjacent rule. The lower mark is 385 plus or minus 1 millimeter. The ball passes the top mark at this time 1.5 plus or minus 0.02 and passes the other lower mark at that. The constant speed of the ball is calculated by subtracting, as we can see, which is 135 millimeters per second. What expression calculates the fractional uncertainty in the value of speed? So speed is equal to the distance divided by the time. So it means the fractional uncertainty in speed is going to be equal to fractional in d plus fractional in a time, because speed is distance over time. Let me just write distance divided by time. So the absolute uncertainty in S is going to be for distance. For distance, we shall first add 1 millimeter plus 1 millimeter, which makes it 2 millimeters. So that is going to be 2 millimeters divided by the difference between the two, which is 270, plus for time, we have 0.2 and 0.02, which gives us 0.04, divided by the time, which is 2. That is the fractional, the sum of fractional. Then this will be multiplied by s, the speed, which is 135. So the question is, which expression captures the fractional uncertainties in the value of speed? So if I take this one back, it means it is going to be A, because this is just if I wanted to find absolute, but if there's fractional only, so this is going to be the fractions. The speed of a car is calculated from measurement of distance traveled and the time taken. Speed is distance over time. So what is the percentage uncertainty in the calculated speed? So we just want percentage uncertainty. So percentage in S is going to be percentage in D plus percentage in the time. So for D, it is 2 divided by 200, plus for T, it is 0.2 divided by 10, and this will be times 100 to change it to percentage. So this is 2 divided by 200 plus 0.2 divided by 10 times 100, which is 3%. So the answer here is going to be D. The uncertainty in the value of momentum of a trolley passing between 2 points X and Y varies with the choice of measuring devices. Measurements for the same trolley made by different instruments were recorded. Distance between X and Y using a meter rule. Distance between X and Y using a meter rule with millimeter divisions. Timings using a wristwatch to the nearest 0.5 at X equals 0.0 seconds and at Y equals 4.5. Timings using light gates to the nearest 0.1 second at X equals to 0.0 and at Y it is 4.3 seconds. Mass of the trolley using a balance to the nearest gram, and it is 6.4 times 10 power negative 2 kilograms. mass of the trolley using a balance measuring to the nearest 10 grams. It is 6 times 10 power negative 2 kilograms. Which measurements one of each quantity measured lead to the least uncertainty in the value of momentum? So momentum is mass times velocity. And velocity, so this is going to be mass times velocity, which will be distance over time. So which measurement one of each quantity measured lead to the least uncertainty in the value of momentum? So the uncertainty in momentum is going to be that of mass over m plus that of distance over distance plus that of time over t. So which measurement one for each quantity measured lead to the least uncertainty in the value of the momentum of the trolley? So when I use distance between x and y using a meter ruler measuring millimeters values, that means the distance has the uncertainty is smaller here. The uncertainty is going to be smaller there because it has a smaller least count. So that one gives a smaller uncertainty in the value of m. Then when I use light gates, they are measuring a small value. They are measuring to a smaller value. So that means the light gates will make the value of time have a smaller uncertainty. So this is going to be fine. Mass of the trolley using a balance to the nearest grams. So this one makes the uncertainty in m very small. That is fine. So our answer is going to be 2, 4, and 5. 2, 4, and 5 will give a least uncertainty. So 2, 4, and 5. The Young modulus of the material of a wire is given by that expression. The wire is extended by unknown force and the following measurements are made. Which measurement has the largest effect on the uncertainty? So we can check. So the uncertainty here in E is going to be uncertainty in F. Absolute in E is going to be absolute in F over F plus absolute in L over L plus twice absolute in D over D plus absolute in X over X. Then this will be multiplied by the value of E. Let's just check the fractions. For F, 0.01 divided by 19.6. So that is 5, this is 5 times 10 power, so 5.1 times 10 power negative 4. Then plus for L. For L it is 0.002 divided by 2.043, which is 9.7 times 10 power negative 4. Actually it is 9.8 times 10 power negative 4. Then plus 2 times for D, 0.02 divided by 0.54 times 2, which is 0.074 recurring. 0.074 recurring. Then plus for X, 0.2 divided by 5.2, which is 0.03, 0.0338. So we see that for D it is greater, so the answer here is going to be the diameter. A micrometer is used to measure diameters of two cylinders. Diameter of the first cylinder is given, diameter of the second cylinder is also there. The difference in the diameter is calculated. What is the uncertainty in the difference? So we just sum up. The uncertainty is just increase, they don't reduce. So it is 0.02 plus 0.03. The uncertainty in the difference is 0.05. We don't subtract them, we just add them. A student finds the density of a liquid by measuring its mass and its volume. The following is a summary of his measurements. They have the mass of the beaker, empty beaker, mass of the beaker plus liquid. That means mass of the liquid is going to be 70 minus 40, 20, which is 50. The uncertainty in that mass is going to be 2 grams. We sum up the uncertainties. Then the volume of the liquid is given. How correctly? He correctly calculates the density as 5.0 grams per centimeters cubed. What is the uncertainty in this value? So we know density is equal to mass over volume. So density is mass over volume. So absolute in density is going to be absolute in m divided by m plus absolute in V divided by volume, then times the value of density. So for m is going to be 2 divided by 50 plus volume 0.6 divided by 10, then this will be times 5. So it's check the calculator, 2 divided by 50, that is the mass, plus in volume 0.6 divided by 10, then times 5, which gives us 0.5. So the absolute is 0.5 grams per centimeters cubed. So that is 0.5. A fixed quantity x naught is measured many times in an experiment that has experimental uncertainty. A graph is plotted to show the number n of times that a particular value x is obtained. Which graph could be obtained if the measurement of x naught has a large systematic error but a small random error? Large systematic error means the average is not the true value. Small random error means the peak is narrow. So we look. So here there is no systematic error because the average is the true value. No systematic error because the average is the true value. Here there is a systematic error, here there is a systematic error. But they said large systematic error but a small random error. So this means the answer is C because here the peak is narrower than this one here in D. So this is a narrow peak meaning a smaller random error, but the average is not x naught, meaning there is a large systematic error. A quantity x is to be determined from the equation x is equal to p minus q. P is measured as that, q is measured as that. What is the percentage uncertainty in x to one significant figure? So let's first find the absolute uncertainty in x, which will be 0.02 plus 0.01, which is 0.03. We don't subtract the uncertainties. So percentage is going to be 0.03 divided by x. X is 1.27 minus 0.83, which is 0.44, then times 100, 0.303 divided by the answer, then times 100. 0.033 divided by 0.44 times 100. So that is 6.8, which is approximately 7. So this is 7%. Which experimental technique reduces the systematic error of the quantity being investigated? Adjusting any ammeter to remove its zero error. Removing a zero error, that is systematic. A student makes measurements from which she calculates the speed of sound as 327.66 meters per second. She estimates that her result is accurate to plus or minus 3%. Which of the following gives her result expressed with the appropriate number of significant figures? So 3 plus or minus 3% is 3 over 100 times 327.66. 3 divided by 100 times 327.66. So this gives us approximately 10. So this is 10 meters per second as the uncertainty to one significant figure. So the answer should also end with 10. So the answer is going to be C. A steel rule can be read to the nearest millimeter. It is used to measure the length of a bar whose true length is 895. Repeated measurements give the following readings: 892, 891, 892, 891, 892, 892. So they are not accurate because the average is not 895. Are the readings accurate and precise to within 1 millimeter? The average of this is around 2 to 3 millimeters. It is actually 3 millimeters away from 895. Results are accurate within 1 millimeter. This is when it is yes, that is not true. They are not accurate. Then results are precise to within 1 millimeter. Let's see the range. The range is 891 and 892 minus 891, which is 1 millimeter. So that is true. So the answer is B. They are not accurate to within 1 millimeter, but they are precise to within 1 millimeter. A student measures the time t for a ball to fall from rest through a vertical distance h, knowing the equation h is equal to a half gt squared applies. The student plots the graph shown. The graph is root of g. The graph is root of g of h versus um, t. Okay. Which of the following is an explanation for the intercept on the t-axis? This equation shows that the graph will not have an intercept. If there is an intercept, then there must be a systematic error. So air resistance has not been taken into account for large values of h, not at all. There is a constant delay between starting the timer and releasing the ball. Okay. There is an error in the timer that consistently makes it run faster. I think that is true because it is showing that the time is always greater, always going to be higher. So there is an error in the timer that is on the x-axis. There's an error in the timer that consistently makes it run faster. So there is a positive zero error, which is a systematic error. So the answer is going to be C. The power loss in a resistor is calculated using that formula. The uncertainty in the PD is 3 and the resistance is 2. What is the uncertainty in P? So percentage uncertainty in P is going to be twice percentage in V plus percentage in R. So that is 2 times V, which is 3, plus R, which is 2. That is 6 plus 2, which is 8. So the answer there is 8%. In a simple electrical circuit, the current in a resistor is measured as this one. The resistor is marked as having a value of 4.7 plus or minus 2%. If the values were used to calculate the power dissipated in the resistor, what would be the percentage uncertainty in the value obtained? So power in terms of, we have current and resistance. Power is equal to I squared times R. So the percentage in power is going to be twice percentage in I plus percentage in R. So this is going to be 2 times for I, 0.05 divided by 2.5 plus for R, which is 2 divided by 4. No, for R it is percentage, so I'll just say plus 2%. So this is going to be times 100, then plus 2%. So this is 2 times 0.05 divided by 2.5, then times 100 plus 2%, which gives us this percentage as 6%. So the answer is 6. Boy throws a ball vertically upwards. It raises to maximum height where it momentarily It is momentarily at rest and falls back to his hands. Which of the following gives the acceleration of the ball at various stages in its motion? Take vertically upward as positive, neglect air resistance. Of course, at maximum height, velocity is 0, but the acceleration remains constant. So where you see that the acceleration is 0, it means that one is ignored. But since it was moving vertically upwards, acceleration is negative at all points. That is in kinematics. So the answer is automatically B. The resistance R of a known resistor is found by measuring the PdV across the resistor and the current I through it, and using the equation R is equal to V over I. The voltmeter reading has a 3% uncertainty and the ammeter reading has 2% uncertainty. What is the uncertainty in the calculated resistance? So percentage in R is going to be simply percentage in V plus percentage in I, which gives us 3 plus 2, which is 5. So the answer is C. So that is 5%. The resistance R of a resistor is determined by measuring the PdV across it and the current I in it. The value of R is then calculated using that equation. What is the percentage uncertainty in the value of R? They gave us V and I. So percentage in R is going to be percentage in V plus percentage in I, which is equal to, for V, 0.05 divided by 1.0 plus 0.01 divided by 0.50. Then this will be now times 100. So this is 0.05 divided by 1 plus 0.01 divided by 0.5, then times 100. So that gives us 7%. So this is 7.0%. So the answer is C. 4 students each made a series of experiments of the acceleration of free fall g. The table shows the results obtained. Which set of results could be described as precise but not accurate? Precise, the range must be very small. So let's see, the range here is going to be 9.84 minus 9.79. We're checking precision. 9.84 minus 9.79. So this is 0.05. Then here we have 10.12 minus the smallest is 8.94. So this is 1.18. Then here the highest is 9.45 minus the smallest is 8.76. The range here is 0.69. Then here the highest is 8.5 minus the smallest, which is 8.41. The difference is 0.09. So this one has D is the most precise. But of course the average of D is less than G is supposed to be 9.81. D cannot give us 9.81, but at least we see that the values are precise. So the answer is going to be D. They are precise but not accurate because the average is not 9.81. A student carries out a series of determinations of the acceleration of free fall g. The table shows the results. So we know that these values are not accurate at all because g is supposed to be 9.81 meters per second squared. So where we see accurate, we cancel out that one because they are not accurate. Then we check precision. Are they not precise? Let's check. At the range of these values, the highest is 4.9293. minus the smallest, which is 4.88. 4.93 minus 4.88. I think this can be considered to be precise, 0.05. They are close to each other, so they are not accurate, but we can consider them as being precise. Not accurate, but precise. A quantity x is measured many times. A graph is plotted showing the number n of times a particular value of x is obtained. X has a true value x naught. Which graph could be obtained if the measurement of x has a large systematic error? Here there is no systematic error because the average is the true value. No systematic error, the average is the true value. So those don't answer that question. Large systematic error, here there is a systematic error, there is also systematic error here. Large systematic error, but small random error. Small random error means values are precise, so the peak must be narrow. Therefore, the answer would be C. Here the peak is wider, so there is a large random error. A thermometer can be read up to accuracy 0.05. The thermometer is used to measure the temperature from 40 to 100. What is the percentage uncertainty in the measurement of the temperature? So, first of all, the temperature raised there is 60 degrees Celsius. Then the uncertainty in 40 is 0.5. The uncertainty in 100 is 0.5. So total uncertainty is going to be 0.5 plus 0.5, which is 1.0 degrees Celsius. As a percentage uncertainty in temperature is going to be 1 divided by 60 times 100. 1 divided by 60 times 100, which is 1.6 recurring, which is 1.7%. So the answer is D. 4 students each made a series of measurements of the acceleration of free fall. The table shows the results obtained. Which student should obtain a set of results that could be described as being precise but not accurate? I think we have answered a similar question. We say the answer is D. The values are precise, they are close to each other, but their average is not G. G is supposed to be 9.81. The last row cannot give you 9.81 even if you obtain the average. So they are not accurate. The density of a rectangular block is determined by measuring the mass and linear dimensions of the block. The table shows the results obtained together with their uncertainties. We have the mass, length, breadth, and the height. The density is calculated to be 250.5. What is the uncertainty in this density? So density is going to be mass over volume, which will be mass over the length, breadth times the height. Length, breadth times the height. So absolute in density is going to be absolute in m divided by m plus absolute in L divided by L plus absolute in the breadth divided by breadth plus absolute in height divided by h, then times 2.5. So this is going to be for m 0.1 divided by 25 plus for L 0.01 divided by 5 plus for B 0.01 divided by 2 plus for H 0.01 divided by 1. Then this is times 2.5. So we have 0.1 divided by 25 plus 0.01 divided by 5 plus 0.01 divided by 2, 0.01 divided by 2 plus 0.01 divided by, of course, that is 1 times 2.5, which gives us 0.05. So that is automatically C, 0.05 grams per centimeters cubed. The measurement of a physical quantity may be subject to random errors and to systematic errors. Which statement is correct? Random errors can be reduced by taking the average of several measurements. That is true. That is the correct answer. I mean, the rest may be not correct. Random errors are always caused by the person taking the measurement, not at all. Some of them are unavoidable. A systematic error cannot be reduced. We can eliminate it. If we know the zero error, we can remove it from every measurement. A systematic error results in a different reading each time the measurement is taken, not at all. For the same measurement, it will be the same reading but above the expected value or below the expected value. A mass m has acceleration a. It moves through a distance s in time t. The power used in accelerating the mass is equal to the product of force times velocity. So that is ma times velocity. The percentage uncertainties are 0.1 in m, 1% in a, 1.5 in s, 0.5 in t. What is the percentage uncertainty in the average power? So percentage in the power will be percentage in m plus percentage in a plus percentage in v. So in m it is 0.1, in a it is 1, in s, in v, v, this is going to be ma times v, which is distance s over time. So this will be, instead of v, I will put there s. So plus percentage in s plus percentage in t. So plus the percentage in s, which is 1.5, plus percentage in t, which is 0.5. So 0.1 plus 1 plus 1.5 plus 0.5, which gives us 3.1%. Last but not least, a student uses a digital ammeter to measure a current. The reading of the ammeter is found to fluctuate between 1.98 and 2.02 amperes. The manufacturer of the ammeter states that any reading has a systematic error of plus or minus 1%. Any reading has a systematic error of plus or minus 1%. Which value of current should be quoted by the student? So let's first find the average. Average current is going to be 1.98 plus 2.02. 2.02, and this gives us divide by 2. So the average is 2.000, as many zeros as you want, amperes. So the minimum value, I'll call it current minimum. The minimum value, because this one is going to be, of course, the smallest is 1.98. So the minimum value is going to be 1.98 minus, we subtract the uncertainty, which is 1 over 100 times 1.98. So let's see the minimum value. 1.98 minus 0.0198. So the minimum value is going to be 1.9602 amperes. That is the minimum. The maximum value we expect is going to be 2.02 plus. We add the uncertainty 1 over 100 times 2.02, which is equal to, this is going to be 2.02 plus, which is going to be 0.0, I think 0.0202, which gives us the maximum value is going to be 2.0402. 2.0402. So the uncertainty in the current is going to be 2.0402 minus 1.9602, and I will divide this by 2. So this will be that minus 1.9602 divided by 2, which is 0.04. So this is going to be 0.04 amperes. So the answer here is going to be D. So that is the end of errors and uncertainties. You see that many questions have been repeated. I tried to eliminate those which have been repeated, but I couldn't read every question when eliminating them. Therefore, you must have learned something from this, and I hope we meet in another chapter. In any case, when you see that I've made a mistake, you can inbox, you can write a comment, I don't mind. You can criticize the content, there is no problem. You can always write to me in case you don't understand anything and I try to rectify. All the best. See you in another chapter and bye bye.